Right, so who's happy there? Thanks for letting me know. Then I think the Zoom though won't see the dot camera, so that's not a problem. I'm not sure what they see when that happens. This thing's running all right, yes. It's on backlit. Anyway, so someone asked about the okay. That's okay. All right. Someone asked about the Gibbs duum, which is the equation if you say
sorry, you're being out of focus.
okay. Auto tune? No. Can't freeze menu.
Oh. So there we go.
Yeah, actually. So someplace here. So it ends up that, I mean, in the end, it's going to be the chemical potential. So you have the partial, the free energy of component I, say you have like A plus B mixed, or this could be the liquid and the vapor in equilibrium, the Ni, and then holding like Tp, and then Nj doesn't equal I. So all the other components or all the other phases held constant. That's the chemical potential of I, and that's also called the partial molar free energy, Gibbs free energy. In other words, the derivative with the molar is the partial molar. So you could have a partial molar enthalpy and entropy too, and volume, and like density or whatever. You can put a bar over it. So this gets confusing if you're doing calculations. You need to know which one's partial molar and which one is a number. So this partial molar value would be an intrinsic value, and it was like temperature or pressure, and the free energies is an extensive parameter, intensive, extensive, or because one is going to be, you could have so much of this like volume, whereas this thing's just a number, just describes a state like temperature, pressure, right? And if you write the write the free energy like we had dg, so that's extensive, like the amount, and then it's going to be minus s dt plus v dp, right? So these are intensive and those are extensive, right? Then you add in, and then you add in this term. So this doesn't work that way. So you add in the dni mu I. So that's extensive, and this is intensive, like mu I is intensive. So that kind of messes things up, right? First off, so that looks kind of weird. Like if you look in the table, it's a table of all magnetism and electrical field and charge, three other components, and they're all extensive, intensive. Yet this term isn't like that because it's anyway. So that's number one. That's kind of weird. And then if you say, you're going to say I have G, and that's going to be the number times mu I, because this is the partial. So if I multiply the partial by the number, I get the whole, right? So that's got to be how it works. So if you do you recalculate that and do the total derivative of this, you get dni mu I. So the sum of those would be like A if it's two component, and then plus na d mu A, and the same for B, right? So you have two terms here, dni mu I, and then na d mu A, and this is mu I dni. So that these two terms are the same. So this is dg, and you equate those two terms drop out, and you end up with just this expression that number of moles of A d mu A plus the number of moles of B d mu B equals this minus s dt plus VdP, but that would be the Gibbs-Duhem equation. So you have this derivative of the chemical potential, and that's in the right form. Like this is extensive and that's intensive. So it starts out, it's kind of, it looks like it's a wrong form. If you do that little switch, you get the right form, I guess. So you get extensive, intensive for the two. And then if you say a constant temperature and pressure, you can use that to determine the chemical potential, the two phases as they relate to each other. So that's useful in writing phase diagrams. That's one of the uses of it. But there's a lot of uses of this equation. It seems like an odd equation. It's like complicated. And it's, but basically, this equation ends up being able to answer a lot of questions. Like if you have, I mean, this one paper that's on the web page where they have nanoparticles and they can calculate the pressure of a nanoparticle with its size by something like the Laplace equation to get the how much pressure is in it. Then you can say like, well, if the pressure changes and the chemical potential changes, it would mean the composition, say at the surface of a nanoparticle, would be different than the bulk. You can calculate that composition using this equation. So the equation is useful in odd different circumstances, like quite a few different odd different places. This Gibbs-Duhem shows up and things are totally unrelated. So that's why it's put into the first chapter, and it's usually given early on, and it's never really given, and I'm not really giving you any background for why I use it either. But when we get to phase diagrams, we'll use it to, I mean, I'll just show it to you, calculate the activity coefficient. Like if you have the activity coefficient of A, then you calculate the B's from that equation, because the derivative, this d mu A becomes d gamma, like the activity coefficient for the, so like xi gamma I gives you AI, the activity. It's activity coefficient. So that's replaces composition. We have a two-phase mixture. Anyway, so it's mentioned here as kind of like, anyway, I'm not sure that answers. Somebody asked why when you get to the total derivative of G, you don't have S and V in it. And I mean, you don't have it because this is just a definition of the partial free energy, and that doesn't need S and V. That's just the partial of the free energy is just going to be the number times that sum gives you the free energy. That's just the definition of it. It's just a way to take a extensive parameter and make it into an intensive parameter, like temperature versus volume. So you can convert the two if you make it specific volume. Right? So molar volume or something. Anyway, I hope that probably confuses things more than what they were already confused, but any questions on that? I don't know that, I'm not sure that really, hopefully it answers the question, but I think it doesn't really give you much of a warm, fuzzy feeling. But maybe you can't help that. I don't know. Anyway, I thought I'd do that. And then I wanted to go through so it's kind of out of the way. And I wanted to go through the homework, like whatever all right, so that's why I have multiple windows here. So everyone did okay on the homework, but mostly it was like 85 or something. Probably, I didn't look at it gives the average in the thing, Then someone got 100. One group got 100. Everyone else got 8. One group got 70 something. But there's going to be 14 grades, so it doesn't matter much. And you have switch groups. So whoever the 100 group guy is, or woman, person will go to your group at some point, and then if you're like low end or whatever, so it'll even out. I think it'll even out. So, but I'm trying to make it a little bit pretty difficult to get an A. In other words, of the 25, maybe 5 would get an A, say something like that. That would be like normal. It's possible everyone gets an A, but basically normally. So make it a little bit of you have to get over things. So anyway, that's the deal. So the question, so this one, I think most people kind of got okay. Actually, people just didn't define, like it says define, they just didn't define sometimes. And mostly people got this okay. And then I guess it's kind of a weird question, so I was trying to get you to kind of come up with an argument here. So it depends on, it's kind of a judgment if argument was good or not, like if it made sense. If it totally didn't make any sense, like the worst thing is if you went and just copied some stuff from the internet and then just pasted it together, so there's no coherency to it. So it's like blah 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 blah, but it doesn't get to any point. That was maybe like 1/4 of the people did that. So that's a bad answer. I guess if you want to see, like ChatGPT is pretty good. You can ask it these questions. You can say, look at this paper and then give it that question, and it'll give you an answer. That's usually pretty good, you know. I'd recommend like looking at it and seeing how, because it can teach you how to give a logical answer to something. Like it's asking you a question. Is this a state parameter? And then what ChatGPT will do is like, first it'll go through like a paragraph defining what a state parameter is, which is what you should do too. And then it'll go in and say like this paper, it isn't really a state parameter or whatever. Or the problem with it is that ChatGPT will always give you a non-committal answer. I'm looking for committal answer. So it'll always say like it could be or it might not be. And it'll give you like the reasons why it is and why it isn't, but it won't take a stand like I am a Republican, you know, like this is the way it is. And I'm looking for you to say like, I just don't believe that, you know, and then so you can become a scientist and justify your arguments. Anyway, but still, it's good to look at what that program does, you know, because it gives you a framework on how to answer something, like how you should go about, like you look at it and it's a blank page and it's pretty shocking. Like, how am I going to answer something like that? I have no idea what's going on. And if you look at what ChatGPT does, it never does that. It never does like blank page. It says like, find the terms, define the terms, and it does it robotically, you know. And then it's going to go like, how does this fit together? And take the paper and piece together all the information from it, and just like spit out something that sounds pretty good. It sounds like what everyone else would say on the internet, I guess. But basically, it's pretty good, right? So usually, like I've given it qualifier questions, and it's passed it every time. Put it that way, with like a high score. So I mean, it's pretty good to kind of see how it's doing. The way it thinks, like it thinks the way you should think, like logically. You know, you should be kind of logically looking at a question and taking it apart. So I think you should use it to, but if you use it and it's your answer is ChatGPT, you should say like, my answer is ChatGPT, and I agree with it or whatever. You know, just say something that isn't like that way. It isn't exactly cheating. You know. So, but mention that you used it. I don't care if you use it, but basically mention that you used it. And then you kind of maybe say something about, I understand what I was talking about. Anyway, so this B part, so it has to do with this figure. So this is kind of important. So he's got the state functions here. He's got density, and he's got some kind of thing. It's like kind of like someone said it was enthalpy. Anyway, so over here he's got the two states. One is not a first order transition. The other one is a first order transition because he goes through this two-phase equilibrium or something here, right? So anyway, the blue is the two-phase and the red is the single phase. When you have red, the state functions are continuous. When you have blue, they go through this jump, right? So the critical point is the black one here, which is between the two, like the first place where you see whatever the hump in this shows up. Anyway, so this is direct information that's a first order transition. Like you have a jump, and he claims there's a jump here. There's not a jump there. So you could argue like that's kind of weird. Then these things are something else though. So what are these? These are all derivatives of the state functions. Like Cp is a derivative of the heat capacity of the enthalpy, dHdt, right? And the compressibility is dVdP. So it's a state versus some intrinsic parameter. And then this is volume with temperature, right? So what happens to the derivative of, so density is more of a volume, density goes through a jump, volume goes through a jump. So what happens to the derivative? It's got a value at low pressure, it's got a value at high pressure. And right at this point, like it goes to infinity because it's not defined, right? So it goes through a step, so the derivative is infinity. That point. So if you plotted the slope of this, you expect to see a number, and then infinity, and then another number, a different number, right, above and below the transition. So because the density would be different above and below, and the rate of change of density, the pressure would be different above and below. So you'd expect to see two constant values and an infinity in between. And in experiments, I guess it's never really, you can't see infinity, so you see this kind of spike thing show up. Right, so these are all, I mean, I think one group said this is a derivative of the state functions, and that's going to show us, someone said pretty close to that. That's what you should be looking for first order. For second order, the density is continuous, kind of like maybe the red line, and then this thing shows a step function. So the derivative shows a step function. So then the second derivative shows a spike, like infinite, not defined. So first order, this shows a step, this shows a not defined, and then second order, this is continuous, and then this shows a step. Second order transition, like a glass transition, is the standard one. And then I guess ferromagnetic, paramagnetic is first order, and ferroelectric, paraelectric is second order. So the magnetic and electric transitions are, glass transition is what second order is usually, like when you have form of glass. So it's got a continuous density, then something like the heat capacity will show a step. Right, and then this was kind of too much, but basically the Ising model is this grid model where you take a grid, and then it's for magnetism, and you have arrows. So it's a ferromagnet. So if you put a field on it, they align. Okay, if it's paramagnetic, then they randomize, and then you can see the transition by changing the temperature. So it'll be a thermal transition, and then so you measure the energy of the system. So in other words, two parallels next to each other is one energy, and then opposites a different energy. You calculate the energy, and then you calculate the Boltzmann factor. So the energy by minus energy over KT, exponential of that gives you kind of a probability, like a number between 0 and 1. And then if the energy drops, so you do a random change of the system, the Ising system, and then so it's basically the Metropolis Monte Carlo uses the Ising model. Ising is this grid thing with arrows, and the Metropolis thing is the calculate the probability, and then say if you accept or don't accept the change that happened. And using that, you can get a ferroelectric to paraelectric transition to happen on a computer. Right? You can see it happen, and you can also see some other things happen. So that it's a pretty simple system. We'll look at it later on, but basically, this is the Ising model for this weird transition that he has, and he says it matches it. So that's kind of somewhat of a standard for seeing a first order transition. So it matches it. So that's kind of what it shows it. Anyway, it's pretty involved. The thing is, like, so you're going to find a paper, and then some of it you know, and some of it you don't know at all, right? So this is how you learn things. Like, this is how the future of your life, you're going to learn stuff. So whether you want to ignore the stuff you don't know and try to read on and piece it together, or if you want to look at every little tidbit and then figure it out, like what is the Ising model, or go to the wiki page, whatever, and it kind of tells you, and then figure out how it fits in here and how it has to do with second order transition. See the steep learning curve at the start, but if you start doing that with every paper you pick up, then eventually there's a limited number of things people talk about.
You mean you does not pull information to solve the questions in the reference and articles? You does not provide.
It's not just the citations, but he just flat, like, you're expected to know what the Ising model is. That's what he assumes in this paper. And this is in Nature, so he's defining, so in other words, material science is a field. How is a field of material science defined? It's defined like this. If I say Ising model and I expect everyone in the room to know what it is, then everyone in the room has to know what it is, and that's the field of material science. And tomorrow it might be something else, right? So in 50 years ago, it was something else. So it changes. It isn't a fixed thing. So that means you always have to be looking things up. So anyway, and I didn't take points off you didn't know what the Ising model was. I'm just saying this is how you should be looking at things now in your stage of your career. It's a steep learning curve, and it can be frustrating. And the natural inclination is to just zip over stuff and say, forget about that, and see if I can piece something together, and then make something up, and then Google it and piece it, and that's it. Boom, out, done. So a better way to do it is to say, like, it's a steep learning curve. It's going to be frustrating. I'm not going to know everything right, but I can at least like look and then try to make connections. And then just to pile up the things, within thermodynamics is a huge pile, but they're made up of pieces, and you can get the pieces from the papers, right? The pieces are there. So you have to look and see. And you're not going to get points for it, but this is how you learn, That's how you're going to put together your understanding of the world, I guess, or whatever the field, or the definition of the field, which you have to define, because it's your generation is going to define the field. The field changes, it's your turn to define it. So anyway, so that's how this works. So that's B. Then so he talks about, so I think, yes. Yeah, wait, your name is yeah something, right?
Oh, my name is Anyungo.
Anyungo. That still hurts. All right, I'll remember it. Okay.
I was gonna ask, so for the grade scale which you've done, I wanted to know, it's not done based off of correctness. It was more based off of.
There isn't a correct answer to these things. It's whether you can make an argument of what you think is correct. In other words, is it ergodic? Well, he explains kind of in one little part of a sentence, without using the word ergodic, why it's ergodic in the conclusion section, where he says that even though the thing's entangled, and the entanglement is the main feature that he's looking at the thing, which would mean it's non-ergodic.
Yes, so
right,
for that, and this might only be me, but when that particular question, is it ergodic?
Mhm.
I went through Webster, the internet, and various other sources, and I wasn't sure if it was just misspelled or maybe just something I never came across, but the way that it was spelled.
Oh, I spelled it wrong.
Okay.
Yeah, I made a mistake with the spelling. It should be with a D or something, and I used a T or.
Yeah.
All right, sorry about that.
A little bit of confusion for me.
Oh, all right, yeah, I put a T here. It should have been D. I noticed that, I guess, at some point. Sorry about that. If it's points, just say, like, send me an email and say, like, oh, because of that messed me up. But
yeah,
I mean, that's fine. That's okay. Sorry, I made a mistake with it. The thing. Anyway, so he makes a point of saying, all right, so it's entangled, right? So it can't be that it finds all the different states because it's stuck. That's the point of the whole thing. It's stuck. So then somewhere at the end of the paper, I think in the conclusion thing, he says, well, it's stuck, and that's the main point of the thing is it's stuck, but it's a kind of stuck where the thing, it's never permanently stuck. So it always can reform and do other things. Like, in other words, it's stuck. It's got this network where it's kind of stuck, but basically the water molecules can just like release and they reform something else. But on average, it's got this thing, this stuck shape. So in that sense, I mean, if you believe that, that sounds like hedging your bets to me. I mean, that sounds like it's stuck. So he's trying to find a way that it wouldn't be stuck, So the things are strong enough bonding that they form a network. And that network is the main feature that you're interested in, but it's not strong enough bonding that it's not ergodic, and that it can't possibly reach equilibrium, which would ruin his entire paper. And he can't prove that. Like, he doesn't give any evidence for that. Like, I guess you could go in and do a dynamic measurement, see how quickly the bonds break, and if, I don't know, you could do something to demonstrate that. But to just say it, which is what he does, that's not very satisfying, I think, for me. But it's not the only field where that happens. Almost exactly the same happens with what they call worm-like myocells. So myocells can form kind of hair, looks like hair, and those things can entangle, and that leads to dramatic viscosity effects, like shampoo. Like when you shampoo is like a classic viscoelastic, but has no polymer in it. Like viscoelastics usually like rubber or something. But anyway, so basically the idea there is also that you can form these entanglements which totally dominate the physical properties of the material, but that they just can like pass through each other too. In other words, to get the thermodynamic equations for it, you have to allow the micelles to pass through each, similar to what he's saying, the water can just like ergodically find whatever happy land, even though it's stuck, right? So there's a lot to it. I mean, basically, I'm just kind of looking to see if you guys could look at something and say something coherent about it, which you did. I mean, I think it was okay. One group did really well, and everyone else did kind of pretty good. So, so that's kind of the way it is. Sorry about the spelling thing. Email me if there's something like that. Just say like, what's going on. Email me right away. Just say like, this isn't anywhere. Like, what is this thing? Anyway, sorry about that. So is that business? You can get more than 100 on these two. Like I give extra points if it looks good. Like something looks like beyond what you're capable of, I give you like some points. But so it's possible that if you got an 85 here, then you could get like 90. You get 110 or something. It's possible. If you I think that's about it. I think that the main thing was this figure C to E. That was kind of straight what you need to know, partly. So any questions? Unless I run that thing. Sorry about that again. But, okay. All right. All right. So that completes this thing. Then all right. So I'm going to move on to this chapter 2 this week. So this is basically looking at transitions. So like just the kind of what the other, it's weird, like the paper was kind of partly what this chapter is about, like the last paper. Anyway, so first order transition, and then so you can see the heat capacity has got this spike in it, like infinity. And it's got two values before and after for first order transition, and the free energy change in slope, but the enthalpy and enthalpy and entropy show the delta, like a heated transition, entropy change and transition. This is for the so he picks all in the book. He's picking all weird, what I think are weird transitions. Like you normally think just the melting point of a crystal, like ice melting, is a first order transition, but speaking, and he does this, I think, for a purpose. So you can see there's like all these different kinds of transitions in materials, right? Especially in metals and semiconductors, right? So he's got semiconductor to metal transition and this nickel sulfur, nickel sulfate kind of alloy, right? So metal means you have the electrons are in the populating the conduction band. So there's bands of energy for the electrons. So if you have like an atom, the atom has orbitals, like the electrons have certain orbitals. And then as they get packed closer, those orbitals kind of interfere with each other. And then they kind of diffract, the electrons and the orbitals kind of diffract off each other, and you end up making these bands, right? Energy bands where the electrons can populate. And the high energy band is a conduction band where the electrons can be free, like they act like a gas. And then you just have the metal nuclei and the electrons in the conduction band are flying around, right? And then, so anyway, if you can have a gap between the populated bands. So there's a Fermi energy level for the material, which is like the average electron energy. It's can be between the conduction band and the kind of occupied bands. So if you excite the electrons, they can pop over that into the conduction band, right? So basically, he's talking about a case where you go through a temperature ramp and then you reach a point where the electrons can hop into the conduction band. So that's this transition in this plot, right? So it's a first order transition, right? So because it's got a heated transition, because it shows these features that are in this plot. Right, so The second order, so the second order is generally so the first order is generally melting of a crystal. He's talking about spot transition. The second order is generally glass transition, right? But he's showing this transition that happens in quartz at high temperature. The quartz is it's a transition where so the density is going to be continuous through this. You know, if you plot density, get a specific volume, right? So there's something weird about this transition. The specific volume is continuous and there was no jump, but basically the thermal expansion coefficient becomes negative at the high temperature, the beta phase of the quartz. So beta phase only exists at high temperature, right? So, but when you get this phase, it thermally contracts, which is really weird, right? The only time you see thermal contraction is in rubber. Rubber or polymers can thermally contract. Like that's a normal behavior because the polymer is made up of these chains. And think about the chain as like a jump rope between kind of tethers. And as the temperature goes up, the thing swings more and more, and it pulls the kind of the tether points together. So it contracts as you heat it up. Right. So rubbers have thermal contraction. So there's this beta phase of quartz. Yes.
So for first order transition and second order transition, when they go into their transition phase, if we were talking about like water, and it goes into steam or if it's turning to ice or whatever.
Yeah, so that's the first order.
Is there a set point of like obviously if you have water in 32 close to freeze, but not all of it freezes. And what is the set point, or how does that regulate it, or is it a limit to where like it just kind of stays to one part and doesn't crystallize anymore? If you don't say.
Well, it should all crystallize. You can, so if any of it crystallizes, it all crystallizes. So, but you can bring it beyond the crystallization temperature and have super cool water. And then if anything happens to it, it crystallizes like instantly. So it should all crystallize. So if you have multiple phases in it, you can get a so if you have water and ethanol, then you can have a gap, right? Yeah. And you can have like solid and liquid in equilibrium with each other.
And I guess the question is more pertaining toward water to gas. So if you have it heated up and to where it starts turning into gas and keep heating it up further, the water doesn't get more hot. It just converts it to steam automatically. The steam is greater, correct?
Yeah, so there's a vapor pressure of water with air. So there's going to be some vapor in the air in equilibrium with the water, like always. So it's a two-phase system. But it's not pure. It's not pure water. It's got air. It's like the air phase and the water liquid phase, right? So you can accommodate some of the vapor, water, and the. Let's see. That's not true. No, you're right. You'll have an equilibrium between the two. Yeah, and it depends on the enthalpy that you put into it. So you need the phase diagram to talk about it. Yeah. Like if you have a piston and you fill it with water, just water, and you pull a vacuum on it, then some of it will vaporize. There'll be equilibrium with the liquid and everything. That's true. So what was the question again?
I wanted to know does it reach a limit or does it stay constant at temperature? So for Celsius, I think water better at Fahrenheit, but for Celsius at temperature, right? And
for boiling, yeah.
Yes. If you put water on the stove and it boils, and you turn up the temperature to 105.
Right. I mean, you don't actually put heat into it. Right?
Yes, the water doesn't become 105. It stays at where it's at, and it converts to steam, correct?
Right.
Okay.
Yes.
I was wondering if that's what I was saying. If it stays constant, if the water is able to get hotter, even though if it was a bigger volume, I guess. So
yeah. So the heat. Yeah, all the heat that you put in goes into this delta H, whatever it is. It goes into the delta H, and that converts the that delta H converts from liquid to vapor. Sorry. That's the whole question, right?
Yes.
Good. All right. All right. Until you run out of water, and then the vapor will heat up after that. All right. Good. All right. So this is what's in the paper this week. So let me go through this thing. So you want to end up with this idea that you can get a plot of like vapor pressure versus temperature. So you want to know what the vapor pressure is of water, say, right? And you're going to, at different temperatures, it'll have a different vapor pressure. Like when it's hot out, it can hold more water, the air can hold more water, and then basically the relative humidity. So if you cool it down, it will condense out, put it that way. And so it can hold less water, so that it condenses out and makes rain when the humid air reaches colder temperatures. Right. So, but in order to get that, you need to know what the saturated vapor pressure of water is. So you have a certain vapor pressure of water, it's hot out, then you cool the temperature, and then at what point will it rain? You know, so that's kind of the issue here. So anyway, so that was a question that people were interested in knowing, and how does this change with temperature, right? So anyway, so that's kind of where this Clausius-Clapeyron thing comes from, right? In the end, it's going to be this kind of what's called an Arrhenius kind of behavior. So you have a log of the parameter versus 1/t, and the slope of this is going to be something like either energy or enthalpy, right? So like if you plot something like viscosity of a fluid, log of the viscosity of a fluid versus 1/t, and then the slope of this is called the activation energy. That's called well, it's like either Irene rate theory, or it could be like Arrhenius for a chemical reaction. Right, so it's the same function. It's exponential of something gives you something. Right, so like viscosity versus 1/t, it's a straight line. The slope is b is it energy, barrier energy. So for that case, for an Arrhenius, it means you have some process that goes on, like an atom has to go from here to over here, and then to get over here, it has to go through an energy barrier. Like there's a barrier that has to squeeze through a hole, and then going from there to there is flow, and that's what defines the viscosity. So if you have, the idea is that this is the energy of activation for moving the atom, and you end up with this exponential dependence, which is kind of like a Boltzmann function. So it's like some energy over t, and that's going to lead to this Arrhenius plot. And then another way to look at that is this Irene rate theory, which has to do with chemical reactions. So it's not equilibrium, but there's also like a reaction energy, and then you get the rate constant for the whatever's going on. Also log of the thing versus 1/t, and also has kind of a Boltzmann argument to it. Right? And then you have this Clausius-Clapeyron, which is vapor pressure versus 1/t. So you can think about like, oh, the water molecules are floating around and they have to jump out into the vapor phase. So it's activation energy. So it'd be kind of obvious it would be exponential, like similar to Irene and Arrhenius, like the same thing. You know? So anyway, but that's not how they got this function at all. They had nothing to do with that. It's kind of strange that you end up with the same plot. And kind of you can make an argument that that's basically Arrhenius behavior, but the function is totally like different from that. Right? So the function comes from looking at the free energy. So you have two phases, two chemical potentials, so two DGs. This is basically DG/dN. So just say DG, which you can get from this, like DG's SDT VDP, right? So minus SDT plus VDP. Then the two phases that are in equilibrium, like the vapor and the liquid, and you're talking about the component like water. So water is the component. So mu is going to be the component water in the vapor, the component water in the liquid. Right. So alpha and beta are the vapor and the liquid. Right. So the volume of the water in alpha, entropy in alpha, those two have to be equal because the chemical potentials have to be equal. So you have to say that that's equal. Then you end up that there's a dp dt term here. And then if you take S alpha minus S beta, that's this change for the first order transition, the delta S step of the thing, which is vaporization in this case, but it could be other first order transitions by delta V, which is the change in the one over the change in the density of the things. Right. So once you have that, you have delta S, which isn't very helpful. Like delta S, you can't measure. Delta H, you can measure. That's the heat that you turn the stove to boil the water. And this is some other thing. Right. So to get rid of delta S, you say that if the things were at equilibrium, then delta G would be 0. And delta G is H, delta H T minus T delta S, GHTS. Right? So if that's true, then that means that, and that's at equilibrium, so that's at the equilibrium like boiling point for the water. So at whatever pressure you're at, so that's the transition temperature. So basically you can swap out delta S for delta H by the transition temperature. And you can just plug that into this equation. You have dP dt is delta H over T times the vapor pressure. Then since you're talking about a gas and it's going to a vapor and it's like a low concentration of the gas in the vapor, you can say the vapor is an ideal. First, the vapor volume is much higher than the liquid volume. So you can forget about the liquid volume. So delta V is the vapor volume. And second, you can say because the gas is at such a low pressure, it's an ideal gas. So you can say V's RT over P. If you swap this and that, so this is a Clapeyron equation, then you get this Clausius-Clapeyron equation, which looks like, all right, so if you put P in here, dP by P is d ln P. So that's where the ln P comes from. So it's not coming from like a Boltzmann exponential, it's coming from this kind of mathematical manipulation of the free energy expression, change in free energy expression. If you start with this thing, end up with the Arrhenius equation at the end, you know. It's something you'd expect it would behave like anyway. So anyway, so dP over P. So because you have a P here for the volume from the ideal gas, you get dP over P, which is d ln P. And then dt here, and because you have a T here and a T there, that becomes T squared. So dt over T squared is d1 over T. Like the derivative of 1 over T is 1 over T squared, negative. Right? So basically, you can get the ln of P versus 1 over T, and then the enthalpy here, you can get the Arrhenius function by this weird root. Right? We did that in the 1800s. That becomes a basis for a bunch of other, like in engineering. So then you're going to have things like the shortcut. So basically you can say like my two states, so that still leaves like two parameters, two unknowns. Like you need the enthalpy and you need the pressure. There's two unknowns, and you're trying to solve for this pressure, right? So it's basically you need 2 points to solve that equation. And the point that's popular is this point. So if you look at the phase diagram, pressure 1 over volume, so density, and then at different temperatures, right? And you plot it. So you have a point where you're at a certain pressure, or like 10 atmospheres or something, and you have like the water liquid and the water liquid and the water vapor. So this is low density, but the vapor are in equilibrium with each other, right? So, and then at that point, if you're at that density, then you have the two phases existing across the tie line, right? So anyway, so if you add more enthalpy, it shifts towards the vapor state, the low density state. And if you take out enthalpy, if you cool it down, it goes towards the liquid state until you get to the liquid, and then it's going to follow this line up, right, as you take out more enthalpy. So anyway, so if you have that kind of phase diagram, you find out that as you increase the pressure, you reach a point, the critical point, where you make a supercritical fluid, where it's not two things in equilibrium anymore. The liquid and the vapor like converge, and you have a thing that has viscosity kind of like a liquid, but it's got solubility kind of like a vapor, or solubility like a liquid, viscosity like a vapor. It's basically dissolve things in it, but it's got no viscosity. So if you try to stir it, it's like stirring air. Basically, you can dissolve things like plastic. You can dissolve different things in it. So it's kind of a weird state. It's not a normal state. So anyway, like if you put coffee in that, if it's CO2, then you can dissolve off the caffeine and make decaffeinated coffee. right? And then pull the CO2 off and you have nothing left. There's no, I think they use like cyclohexane or something to do it normally, which is like toxic, but CO2 isn't. So you can do it. Supercritical CO2 is the most popular because it's easy to reach like supercritical state. I think it's like 10, like maybe 5 megapascals, so 50 atmosphere or something, but you can get with a little, you can get it with a little piston. Like it's easy to get that pressure. So anyway, so because the phase diagrams look kind of similar, and that this critical point is like the touchstone for them. So basically, you can reduce everything using that critical temperature. And so this T reduced is a temperature divided by the critical. P reduced is the pressure divided by the critical. There's also a density, a volume, specific volume, critical, right? So basically, you can write those things in terms of just the critical parameters, and then you can write like a generalized equation to get the vapor pressure of something that's just based on these reduced parameters, and something called like a fudge factor that has to do with how basically a fudge factor. It's called the eccentric factor, but it's just a fudge factor to get this to work. Right, so you can calculate that empirically, like just with equations that people have written. But anyway, so that kind of Clausius-Clapeyron leads to things like this shortcut vapor pressure method to calculate pressure of things. So this is kind of like mostly used in chemical engineering, but if you look it up, this thing is, there's a bunch of papers on this Clausius-Clapeyron dealing with atmospheric science and cooling of the earth. And there's a bunch of papers on clathrates, which is what the paper is this week. So basically, we had the tetrahedral structure of water, right? So water makes this kind of tetrahedron. The way it shows in here. Let's see. Let's see if I can get over to this guy. So it shows here somewhere. Maybe it doesn't. Oh, yes, it doesn't. Anyway, water forms a tetrahedron. The way the oxygens and hydrogens hook together, it makes a tetrahedron like the balls we had last week, but with molecules. And that, because it forms this kind of geometric structure, it's possible that it can make like a cage, where it can trap things like methane within that cage. All right, and it can trap hydrogen and CO2. Those are the main things that they look at, I guess. So methane's important because it's a greenhouse gas. It's like the methane, in fact, is trapped at the bottom of the oceans under kind of 10 megapascal or 55 megapascal or something like that range. And then at cold temperatures in these clathrate water cage structures. And in the middle of the cage is a methane molecule. So methane has something like 100 times the greenhouse gas of CO2, but it's got a limited lifetime in the atmosphere. So it's an advantage to methane and a big disadvantage. In the short term, it kills all life on Earth. In the end, it goes away. Like it's not like CO2 is going to last like 1,000 years. Methane's like 50 years. But in the meantime, in the 50 years, everything dies because it'll just kill everyone, right? So clathrate gun brings us to the clathrate gun hypothesis, which is real. I mean, it's kind of funny, but it's real. So basically, if the oceans heat up by a degree, there's these clathrate crystals at the bottom, and they'll transition and release all the methane. And they've trapped all the methane forever at the bottom of the ocean. It's basically, that's the end of the Earth when that happens. So if the oceans heat up, basically, like I think it's something like a degree, then this supposedly will happen. And it's already happening, like in the permafrost and stuff. Like there's places where the methane, anyway, it is happening. So far we're not dead. But I suppose we'll have a little bit of advance warning, but maybe not that much. Anyway, historically they go through and find out where these clathrates like explode. The other thing is that you can trap CO2 in this. So if you want to try to prevent the CO2 pollution, you can use the same technology to trap CO2 and lock it at low pressure in like a mine or something somewhere. Right, so you'd use clathrates to trap CO2. The third area is like hydrogen storage. So the problem with hydrogen is that you need high pressures to store it and do anything with it. Make it liquid hydrogen. It's like what is it, like 80 megapascal or something, some huge amount of pressure, right? Nothing that you could possibly use. So there's a couple of routes to it. One is clathrates. One is to convert it to ammonia, which is like propane. So same pressure as propane. So you can make like a propane pipelines to transport ammonia. And you can burn ammonia for fuel. But anyway, so the clathrates are another way you could store hydrogen in kind of a compact crystalline form at room temperature at moderate pressures. Right, so it's an interesting subject. There's a bunch of different angles to it. So anyway, this Clausius-Clapeyron is one of the uses in the literature currently. There's like clathrates, and then looking at clathrates also form in petrochemical pipelines, so it's a problem. You form solid crystals in the pipeline, it clogs it and it blows up, type thing. So there's money in it, I guess, looking at clathrates theoretically. So there's people working on it. I'm not sure. I didn't see anybody getting rich off it, but so this is just showing Clapeyron prediction, and then first order phase transitions, kind of just so this is melting of different crystals and showing how this matches up with it. Let's see, what else do we got here? Time. So what is this? Let's see what else I have. It's a paper where they're using to look at surface absorption of gases using the Clausius-Clapeyron equation. I think it's a paper we used. It's like 2020, so we used it in the past. Oh, then there's this other equation. So there's a bunch of equations like the Clausius-Clapeyron equation, right? I mean, for one thing, there's all the Arrhenius and Irene rate laws, and then there's this thing called the oops, where did I lose this thing? The Van Hoff equation, which is for chemical reactions, which ends up looking exactly the same, right? In other words, so the Clausius-Clapeyron, and then ln of the reaction equilibrium constant is the enthalpy of reaction over RT squared. It's the same form, right? It's the Clausius-Clapeyron equation, but you get it from the definition. Just say like the definition of the this is just the definition of the chemical equilibrium constant in terms of the Gibbs free energy for the reaction, right? And if you do that, basically you can work out this same dependence, right? You can get the same dependence on as the Clausius-Clapeyron and Scull-Van Hoff equation. So it's like 4 equations that end up with the same functionality, like ln of something versus 1 over t. Clausius-Clapeyron, Van Hoff, Arrhenius, and Irene rate. So anyway, so basically it's almost like you should get used to the idea of seeing something plotted like log of something versus 1 over t is like a natural way to plot things, and then figure out which of those 4 categories your thing most closely matches, right? So if you're plotting something and it's like the thing versus temperature and it's not working and it's like kind of a curvy shape, then try log of the thing versus 1 over temperature. That's like should be your second step, right? Because this is like the natural way things happen, especially things where it's like a rate happening in temperature, it kind of encourages it. So if you see, so a common thing would be like you pick up a paper and they just show like log of something versus 1 over t. So you should immediately think like the slope of that's going to be like either delta H over R or the energy over R, and it should be a straight line. And then deviations from that are because something isn't going right with that model. Like in other words, it's not exactly activation energy that's going into it to make it happen, or some of these assumptions. So there's a lot of assumptions here in the Clausius-Clapeyron. So the question is like, how do you take this thing apart? Is one of the questions. Like how are you going to say like, so in our paper, in this paper, they have a modified form of this, for instance. So how is that put together? So the assumptions here, if you get to Clausius-Clapeyron, is that it's an ideal gas. Like, so if it's a dense gas, like if a clathrate is going to happen, I mean, normally at the bottom of the ocean, it's 30 megapascal or something. Then in this paper, he's doing it at 5 megapascal. So he figures out a way to put in a magic foo-foo dust to make like methane clathrates at room temperature, or hydrogen clathrates. He does all of them. So basically that could be a big boon if you want to have hydrogen powered cars, for instance, and you want to transport somehow dense hydrogen at low pressure. So when you get in an accident, it doesn't just like blow, or you don't need a big steel drum to hold the hydrogen in, right? So you wouldn't want to drive around with 100 megapascal thing. It'd just be pretty dangerous. So anyway, so the assumptions are it's an ideal gas. And then the other assumption is that the liquid in the vapor state, it's only vapor volume, right, to get that equation. So neither one of those works for a clathrate. Like neither one really makes any sense because the liquid, I think neither one really works for a clathrate. So basically you have to kind of consider if he's using the Clausius-Clapeyron and it doesn't work, like those are the reasons it doesn't work. So then how do you go to a non-ideal gas? Like if you want the ideal gas law, how do you get away from that? Right. So the easiest, I mean, the kind of the most common way to do that is to say use a van der Waal, right? So a Dutch guy. So you had PV. So you have kind of that equation, right? Or PV. Right. So you have P is RT over V. Right. So ideal gas means you have these atoms that can just pass through each other. Right. They have no excluded volume. So the first thing you want to do is say, well, that doesn't make any sense. This thing has a volume, right? Say it has a volume B, which is B is the thing that van der Waal used. So he says, like, I have the volume, I have to subtract off B. Right. So what does that do? This number gets smaller, this number gets bigger. So by having excluded volume, I increase the pressure, which makes sense. Like I have less room for the atoms to move around, the pressure has to go up. So that's good, right? But this doesn't, one of the main things, you have a gas and you want to go to a liquid, right? And this equation can never give you a liquid because if things just pass through each other, they have no association at all. And a liquid assumes that the things are going to want to kind of cluster together to form a liquid phase versus a vapor phase. Well, they don't, right? So to get the thing to attract, you put in a thing that's going to reduce the pressure. So you subtract off some number A. So van der Waal uses this A number. And then you say, well, that's going to be, if it's the simplest situation, I have number one and number two interact with each other. That's a binary interaction. So that means it's going to have to be the density squared because two things interacting, that makes it binary. So you'd have density squared as a lead term to that. To divide A by volume squared, and that's the van der Waals equation, which is it's a cubic equation of state. So if you solve it, you'll get two solutions, and then those two solutions allow you to have the two phases. And if you solve that equation, it gives two roots, and the two roots, it actually gives three roots. The middle root's useless, and the two roots are going to be liquid and vapor phase, like if you plot PV. Right. So anyway, so that's a cubic, it's called a cubic equation of state, because if you expand this out, you get a square term in density. And so basically the square term is a cubic equation. Right. So that's the basic equation that you need. And then there's other ways to modify that empirically to make it work better for whatever thing that you want to look at, but Anyway, so that's kind of how you would go about fixing this. Like instead of using the ideal gas law, you'd put in a van der Waals equation or some other equation, and then you get two other parameters. Like, yeah, you have to have two parameters. One would be excluded volume, and one would be this attractive potential that allows you to have a liquid state. Right. So you have to add two parameters to this kind of simple function. We had one parameter before, so you have three parameters. And we have the ideal gas constant and A and B. And A and B change depending on what the material is, depending on how attractive the atoms are. So so anyway, that's another thing about single phase is this phase diagram thing. What else is going on here? So second order, I mentioned second order already, but so anyway, so the first thing in the book, he goes through this business of how you can define like the pressure dependence of the glass transition temperature, say. So he says like there isn't really a different phase form when you make a glass. Like the liquid goes to the glass, the density is the same above and below. So there isn't really at the point of the glass transition, it's not like a two-phase system. Like it's the same. If you take a diffraction pattern of the liquid, diffraction of the glass, above and below the glass transition, it's the same pattern. So the atoms are arranged the same way. So everything's kind of the same. So the difference is the motion of the atoms is kind of like kinetics changes. So things get stuck, and then it makes glass, right? So you can look at that like the change in volumes 0, and then do an expansion of volume, and then these things dV dt, dV dP, that's alpha and kappa. So the isothermal, isobaric and isothermal compressibility and thermal expansion, and that would give you T and P. So the pressure dependence of the glass transition would be just that ratio of those constants that you can look up. Right, if you want to do that. He mentions that in the paper, in the book, right? And then he shows that the glass transition with pressure is linear, and the slope of it is that ratio in this thing. Right, so that's kind of interesting. So let's see, maybe this is a paper that I got somewhere, but basically that's that business. Maybe that's not in the book. Anyway, so this is the way glass transitions looked at least in I mean, there's complex ways to look at glass transition, and there's kind of simple ways to look at it. So the simple way is to talk about this idea of free volume. So the atoms always have some space associated with them, and when you get at some point that space as you increase, so as you decrease the density or decrease the specific volume, increase the density, the space, in other words, the atomic space is fixed. The atom size is fixed. The Bohr radius is fixed. And as the things, as you reduce the density, they pack in closer together, which means that the free volume, the volume that other than the Bohr radius volume, reduces. As you can say, there's two volumes. There's like an occupied volume and a free volume that makes up what a material is. As you reduce the volume of the material, then you're reducing this free volume, basically. And then there's the solid volume is like when you're reach bottom, like there's no more room to squeeze, right? So as you cool it down, you reach some kind of free volume percent. So it's the difference between that volume and that volume is this free volume. And like Simha says, it's 11%. Like when you reach 11% free volume, it becomes a glass. And at that point, everything's stuck. So things like the heat capacity change. So because they can't move as much, they can't accommodate as much heat. So that the heat capacity changes at that, and the slope of volume versus temperature changes. Yeah.
Is there a change in the free volume, or it's at that specific value of free volume?
There's still a thermal expansion coefficient to it. So I think he's saying that the Bohr radius has like a thermal expansion coefficient, and that so you start out with a 0 n Bohr radius, and then it increases with temperature. I'm not sure that's really true, but that's kind of what this implies, right? So the free volume fixes. And then at that point, it's still, the volume still decreases, still has a thermal expansion coefficient, but that's just the core thermal expansion. So things are stuck. So the free volume stays the same after that.
Okay, so it's a fixed value.
It's a fixed value after that, yeah. So if you think about, I like to think about this ground coffee thing, which you guys probably have never seen before. But basically, if you take coffee and pull a vacuum on it, you can make a brick. They sell it, you can buy it that way. You used to be able to, in a paper pack or plastic package. And if you poke that, it's about like the volume increase once you poke it, and then it becomes like a liquid, is nothing, you know. It's less than 10%, I think. But the properties of the thing are completely different. It's solid, like you could kill someone with it when it's brick, and when it's just like a pillow after that. Like you didn't hurt anybody. So anyway, so basically, yeah, there isn't much change here, like when that happens. Like that free volume isn't much to make it turn into like a liquid. Right. So anyway, that's basically this free volume concept. It's more or less it's a little bit of a fluffy idea compared to some of the other glass transition models, which have more to do with like the dynamics and things. They're so let's see. Anyway, all right, to measure this, though, like how would you measure that? Well, you can measure the volume, you measure the specific volume and kind of get an idea about it. But anyway, what people do is they get positrons, which annihilate when they match up with electrons to make nothing, like it's antimatter. And you can get positrons from some kind of metals that gives it off. So you can put that kind of metal next to your stuff, and you can kind of measure the energy given off when the positrons annihilate. Anyway, so this is people do this positron annihilation spectroscopy to measure the free volume for this kind of thing. You can imagine you don't make a lot of money doing that. This is like one of those kind of like esoteric things that people do. Anyway, so that's how people do actually measure free volume that way. So there's some, like for polymers, there's this Fourier-Fox equation that has something to do with the free volume. Like if you have a polymer, so there's a molecular weight dependence to the glass transition in polymers. Like as the chains get longer, the glass transition gets higher, right? So basically the chain ends have more free volume than the chain itself. This is the idea. So the more chain ends you have per mass of the material, then the more free volume you would have, and then it would be closer to the glass transition. So you could say like you have your infinite molecular weight with no ends, and then this kind of end effect thing divided by the molecular weight, because the number of ends would be like 1 over the molecular weight. The bigger the chain has fewer ends than the sample, right? So it's going to be 1 over m. And then this is called the Fourier-Fox equation that lets you kind of calculate the glass transition of a polymer as a function of the molecular weight. And it has to do with this free volume idea too. But anyway, so yeah, this is business. Let me skim through and see what I have here. Let me go to the end and see where this goes. It's phase diagrams, which I can already mention a little bit. Oh, the Landau theory. Yeah, this is going to take a while. Actually, it might go faster than you expect, but these things, just give it a couple of minutes. Let's see, I'm going to hide this. Oh, that wasn't what I wanted. Look at that. All right. So anyway, so magnetism is like the early study of phase behavior. Like first order was all based on magnetism. So when you get into the literature on first order transitions, first and second order transitions, it's all based on this picture. Like they talk, like the last paper, he talked about the order parameter, the M thing. So what's an order parameter? Right, so that came back to this, right? So somehow everyone's going to be talking about order parameters and first and second order transition, the whole idea of an order of a transition, all that stuff came from magnetism. And then there's anyway, so and even the concept of polarization and electrical comes from magnetism. So the magnetism stuff is important to kind of get a picture of what they're talking about, right? So basically you can go from so you can have these magnetic moments. So the arrows are magnetic moments. They aren't atoms, like regions of a metal. So you have kind of electrons can make, because you have the Maxwell equations, right? That give you, not Maxwell equations, it is Maxwell. But you have, if you have an electric current and then you have a magnetic field, like the right-hand rule, so the current goes around, you get a field the other way. Okay, so because of the electrons in atoms and conduction bands in metals, then you can get domains forming in a material spontaneously that have these magnetic moments, right? And generally, they're going to be pointing in all different directions, right? And the size of these are going to be like microns, like 10 micron. So it's not an atom; it's like a region, some kind of region of a metal. Okay, so within that region, you have these domains that are magnetic, right? That have a pole, north, south, and generally, like you think that it would be like it would want to like randomize, right? So it has to be like this. So that'd be like the normal way that it would be. If you put a magnetic field on it, it'll align, right? So this is paramagnetic, and if you put a field on it, it aligns. That's a paramagnetic. So you can also kind of lock in that polarization or magnetization into a structure that where they're naturally just aligned, like a ferromagnetic material. All right, so you can have a transition between these states. That's a first order transition in temperature. So as you heat it up, it'll become paramagnetic. Cool it down, it can become ferromagnetic. Right, so you can see this. People that like arrows and boxes, this is going to be like the perfect thing. So you can just make a grid and put all these arrows in it, and that's the Ising model. That's like the foundation for all the phase behavior, right? So, and then you say, well, what does that have to do with, like, if I take A and B and I mix them, and it's going to phase separate into A-rich and a B-rich phase? Well, you say, oh, then you just replace these arrows by composition. See, people make these jumps that don't necessarily make any sense. So then the order parameter becomes density or composition versus orientation of an arrow, right? So anyway, it gets pretty confusing. Like you're talking about. So anyway, the arrow thing's important to get a feel for kind of at least what ferromagnetic and paramagnetic are. Then, so those two are the most important, right? There's other nuances to this. Like you can have, once they studied this, they realized that you could have dominant, so you could have like a salt or something, where you could have components that are going in one direction, like NaCl. So you have plus and minus, and some are going up and some are going down. Like the Cl is negative, the Na is plus. You're going to have like up, down for the polarization of the thing, right? So that kind of thing can happen with magnetization too in these micron domains. You can get domains, majority domains going up, minority going down, or you can get an even match of the two. Right, so these things can happen also with magnetic alloys, right? So basically, you can have a ferrimagnetic, which means it's got a mix with a dominant one, transition to an anti-ferromagnetic, or it can go from ferrimagnetic. You can transition between any of these. Okay, so some of these will be ferrimagnetic to paramagnetic transition is a second order transition. And this is a first order transition, ferromagnetic to paramagnetic. So if you play your cards right, you can get any kind of transition from this mix of arrows, right? So anyway, so this is kind of where things kind of are going, you know. The order thing, so is that business, So this is the Curie temperature, the Ferro to para, and there's a Neal temperature, the Ferri to para, like this one to that, to para to that one. This to that is this Neal temperature. Oh, Neal temperature. Oh, it's this anti-ferro to para, I guess, is a Neal temperature. And there's Ferri to para also, which I guess is another name, but let's see. My guy has decided to stop doing anything. Oops, there it did something. So this is a second order transition, right? This is the Neal. So you can see it's the same thing. You have a spike. It goes to infinity. It's got a value here, a value there. The heat capacity. It's a derivative of the. So the spike means that the enthalpy went through a discrete transition, right? So, I mean, this is first order, right? You can see that. So, all right. So, anyway, so there's this Russian guy. We got a couple minutes, so he's an interesting character. So Stalin. So this is 1938. And Stalin was in Russia, right? And also they're trying to develop the nuclear bomb, the hydrogen bomb, right? So this guy played a role in all of that, and in this idea of states and order, the order of the transitions, right? So all this came from an insane person, obviously. So he was in a car accident, and like his brain was messed up. So trying to see if his brain was okay or not. And this is supposedly like the questions they asked him, and then it's like, if I answered the right way, you'd think I was retarded type thing. So anyway, so he's kind of quite a character, and he spent time in prison too in Russia, but then he ended up basically developing the hydrogen bomb for the Russians, and in the meantime, he also, I mean, before that, he had developed this order concept, the first order, second order thing. So, yeah. So I guess next time I'll talk about this, the order stuff. And I think we have enough to do that paper, and probably this will drag on until next week, some of this stuff on the single phase thing. But anyway, so that's it. Any questions or anything? Anyway.
So that graph right there represents what kind of?
First. Yeah, first order, because it's got the spike in the CP. It's just the same thing as what we had in that paper. The paper this week, he had a spike. He showed CP, he showed alpha, showed kappa. Like, right? And all three of them showed a spike. So it means it's like a delta function.
So you're saying this is a jump?
Yeah.
It looks continuous to me, but
It's the same thing as what we had. Oh, that's a paper, right? So he's got exactly the same thing, right?
oh, but this is these are derivatives.
No,
right?
this is the derivative of enthalpy with temperature. And enthalpy is showing something like that thing, like a step functions.
Right. Okay.
So
I
if you
thought it was
take
only a
the-
jump when it was a complete absence of
Yeah,
data
that's
here.
right. The complete absence. So the complete absence one, right?
Right.
If you take the derivative, you get a number there, you get a number here. Right at that point, you get a spike. It's going to go to infinity.
Okay, so this is a
That's a
derivative.
spike. Yeah, this is CP. CP is a derivative.
Okay, got it.
Yeah, and the others, so the other things that aren't derivative are like density, volume, enthalpy, entropy. Right.
Yeah.
And then whatever, like the bottom thing is enthalpy, supposedly.
All right,
The
thank
bottom
you.
thing, yeah.
Same sort of deal, but what is this second order referring to in this? I know what you're saying with first order matching this.
Yeah, if it's second order, it should have this, maybe he's talking about this black circles,
Yeah.
There seems to be like three behaviors here. There's like the
Yeah.
spike.
Yeah,
that
there's
thing,
multiple
that thing
things
down
on the
here.
same graph. Yeah.
Yeah, I'll have to go back and look.
The other question, I guess, when both referring to like this sort of pattern on the graph, or same thing that we've discussed in the homework of those three graphs that showed that. So like, when we talk about the transition itself, so it's kinetics, it's time dependent.
Right.
So how can we, there can be a case where it goes towards the limit, I understand that, but how can we like, how can we possibly define something to be like immediate, because there always is a time transition, there is like it's never like an infinite change.
Right. Like,
How are we,
so
how
if
are
you
we,
measure, all right, if you measure with a DSC, you're gonna take, you're gonna have like two pans and you're gonna heat it. So you heat it at a certain heating rate, right? And you'll see like the enthalpy of you're measuring CP actually when you do that. So you'll see like the integral of this thing will be the enthalpy of transition.
yeah,
So you'll see that thing grows as you heat it faster. And the position of it will shift somewhat. Yeah.
yeah.
So you superheat the solid as you
Mhm.
heat it faster, and but you get a larger signal that you can pick up. So you have to have a finite heating rate, you won't see anything.
Yeah,
So it's
and
kind of a catch-22.
this also goes into this graph here where like I guess my like logical thought process, what I'm getting stuck on is the fact that like you have to have such a fine resolution, if you want to say, of like data points to be able to validate like this, whatever, 10 data points. Like obviously this is like arguable, but like from here to here, it's obviously a direct transition in comparison to this other one. However, like it's still at two different points on the x-axis. Like you can still say like,
Yeah, if
you can't say with
expanded that out,
100% certainty
right, if
that
you took
actually,
more points, it might look like the red one. It's
yeah,
true.
like,
No, there's no answer to that. I mean, it's gonna be like, there's a theory, and you say like it matches the theory, and you can make the argument you're making, you know?
Yeah.
That's a valid argument, you know? And then they have to answer like, this is good enough, you know?
yeah.
So basically nothing's really that cut and dry.
Yeah,
But there is like a framework that you can understand the world by.
yeah, yeah.
Without the framework, you're like hopeless, right?
Right.
So,
But it's, following the pattern of,
and it's easy to question it, but when you actually use it, like all these thermodynamic laws and things actually work, you know?
yeah,
So you'll be surprised that like this stuff actually, it sounds like it's just philosophical, but it isn't.
matches to reality. Yeah.
And matches to reality, and it gives you the ability to predict. Like
Yeah.
a lot of the things that we do every day are based on predictions based on these laws, so.
Yeah.
Without it, the whole society as we know it would collapse. Basically. The click rates would definitely come after us. Yeah. Kill this.